operation principle of RTDs in general follows Ohm's law, that a passing current through an RTD generates a voltage across it. By knowing the voltage, you can determine its resistance. Now, using this table, temperature versus resistance, you can determine the temperature measured. There are two standards for temperature versus resistance tables for PT100 RTDs: the American standard and the European standard, also known as the IEC standard. The European standard is considered the worldwide standard for platinum RTDs. There are three types of wire configurations for RTDs: 2-wire, 3-wire, and 4-wire connections. Here are a couple of references showing the different wiring configurations. The wire colors can vary according to each manufacturer. But here are the standard RTD wire colors. Wire and 4-wire connections. Here are a couple of references showing the different wiring configurations. The wire colors can vary according to each manufacturer. But here are the standard RTD wire colors, according to the International Electrotechnical Commission, IEC 60751. So in general, it's easier to know that this is an RTD if it has more than 2 wires, because thermocouples have only 2 output wires, even though both might look similar. Here are a couple of examples showing the wire colors for RTDs. There are 2 ways to connect thermocouples and RTDs to a PLC. The first method is connecting them to a transmitter that connects to a PLC analog input module. Or the second method, where some PLCs have a temperature sensor module, so sensors are connected directly to them. Transmitters are used to take millivolts from thermocouples or resistant values from RTDs and convert that into a high-level signal like 1 to 10 volts or 4 to 20 milliamps and send data to a PLC analog module. Here is an example of a temperature transmitter by Siemens. So simply, as you can see on the screen, just wiring the temperature sensor, an RTD in this example, into the transmitter unit. The wiring connection diagram is usually shown in the datasheet for both RTDs and thermocouples for different manufacturers. Here is an example from Endreshauser showing where to connect each wire color, red and white, of the RTD to the transmitter pins. Usually RTDs and thermocouples are designed to come with a built-in head transmitter, as you can see here. So many industrial temperature sensors look like this. In this case, the wiring from the transmitter head is connected directly into the analog input module. There are also different designs for the transmitters. Each is used for certain environment and processes, like different temperature, pressure, indoors or outdoors, field placement, etc. Some designs can look similar to a module, as you can see in the examples here. The second method of connecting temperature sensors to PLC is that some PLCs have a temperature sensor module, so simply wiring RTDs or thermocouples to it directly. Here is an example of temperature input module from Rockwell Automation. A pressure sensor is a device that used to measure the pressure of gas, steam, or liquid and convert the value into an electrical signal to send it to a PLC controller. Here are a couple of examples of pressure sensors. Usually, they are called pressure transmitters because they have transmitter attached to them. In general, the sensor consists of a sensing area and a transmitter part. The sensing area measures the pressure force applied to it. The force deflects an internal diaphragm inside the sensing area. The deflection is measured and converted into an electrical output by the transmitter. The conversion of the deflection into electrical signals is based on one of the following principles: a change in resistance, capacitance, or piezoelectric. Each is used for certain application. The sensing principle is usually mentioned in the datasheet. The output of pressure transmitter is either in volts or currents, connected to an analog input module of the PLC. Voltage is usually between 1 to 5 volts. Current is usually between 4 to 20 milliamps. The values, volts and currents, represent 0 to 100% of the sensor pressure range. For example, a sensor is designed to give an output of 4 milliamps when it has a 0 pressure, and 20 milliamps when it has reached the maximum. The same applies for a voltage output. Pressure transmitters usually come with a display unit to show the process pressure when used in the field. The handout of this video is a refresher in understanding pressure definition and absolute pressure and gauge pressure measurements if needed. There are some terminologies used when working with pressure sensors. I will cover a couple of the common ones: range, zero, and span. Pressure sensor devices come with a specific range designed by their manufacturer. Range identifies the minimum and the maximum pressure that the sensor can measure. The minimum pressure is called lower range limit, or LRL. The maximum pressure is called upper range limit, or URL. For example, a range of 0 to 20 psi. Now, operators have the flexibility to make adjustments within the manufacturer range. Let's say I want to use this specific pressure sensor to measure only 3 to 15 psi for my application. The values for the chosen range are referred to as lower range value, or LRV, and upper range value, or URV. So 3 psi is the lower range value and 15 psi is the upper range value. You can see here a demonstration of the pressure sensor limits and the calibrated or adjusted values. The sensor has a range of 0 to 150 psi. The upper range limit is 150 psi, but the calibrated one is 75 psi. Span is the difference between the calibrated lower and upper range values. For example, if the range is 3 to 15 psi, then span is 12 psi. 0 is the smallest pressure at which the transmitter is calibrated. For the same example, then 3 psi is considered our 0. The 0 here does not necessarily mean a zero number, as in 0, 1, 2, 3. But it could be if the range is 0 to 20 psi. So to avoid confusion for the sake of understanding, I will refer to number 0 as a real 0. 0 represents 0% of the sensor pressure range, meaning 3 psi is the smallest pressure the sensor can measure. There are two common ranges that you would probably come across when dealing with pressure sensors: suppressed zero range and elevated zero range. Suppressed zero range, a range that is all above real 0. So always look for the lower range value. If 0 is below the lower range value, you would have a suppressed range. An example would be 3 to 15 psi. This is a suppressed zero range. Elevated zero range, a range that has real 0 part of the range. So if the real 0 is above the lower range value, or somewhere between lower range value and upper range value, you would have an elevated range. An example is -15 to 45 water column. This is an elevated zero range. One of the good practices when working with instrumentation in general, and pressure sensors specifically, is to avoid choosing real 0 as the start point for measurements and signal ranges. The reason for it to differentiate between an actual 0 reading and a device failure. Because when a device has failed in case of any loose wires or loose connection, it would produce a 0 value. If we choose real 0 as our starting point, then we wouldn't know if 0 is a failure or no pressure is applied to it. Now, in order to have pressure sensor device give a certain output value for a specific pressure range, we need to calibrate the device. Calibration is the process of adjusting pressure sensor device in order to achieve a desired output range for a specific input range. Pressure transmitters usually have two knobs that are used for calibration: 0 and span. They are usually located inside the transmitter head. Knobs for the 0 and span adjustments can be two buttons or potentiometer screws, so either physical adjustment or software-based adjustment. Here's an example from Rose mount transmitter showing the 0 and span buttons. Here's another example from Endress-Hauser. 0 adjustment is used for adjusting lower range value, 0. This is how 0 adjustment works. In this example, the input range is 3 to 15 psi, and the output range is 4 to 20 milliamps. Let's take this hypothetical scenario. When the pressure is 3 psi, the output is showing 3.8 milliamps. In this case, we need to adjust the 0 knob to ensure that the output is closer to 4 milliamps. In the example here, once 0 is adjusted a little bit, you see the output now is 4.1 milliamp. Usually this process of adjusting the 0 knob is done a couple of times, basically calibrating the device in order to achieve the proper lower range value. And you would see this calibration table where you have the ideal output and the values you get while calibrating. Span adjustment is used for adjusting upper range value, span, sometimes referred to as the overall gain. So in this case, adjusting the span knob is to help getting the upper range value, URV, back to the ideal value when the maximum input is applied. Here, for example, having 20 milliamps, 115 psi is measured. A combination of the two calibrations would result in achieving a desired output range for a specific input range. Pressure sensor measurements are classified into categories. Here are a couple of them: differential, absolute and gauge, and hydrostatic pressure measurements. Differential pressure means the difference between two pressures, usually called delta P. Delta showing the difference in pressure. P is for pressure. For this type of measurements, it's either having two pressure sensors like the one you see on the left, or one pressure sensor that is designed for differential measurements like the one you see on the right. This type can be used for level detection or for flow measurement in different parts within an industrial process. Absolute and gauge pressure measurement. As the name indicates, measuring the pressure based on the two scales. Gauge pressure sensor shows positive pressure values above atmospheric level and negative values below it. For absolute, it shows the reading in reference to vacuum. Now it depends on your application. This would determine which one to use. If a process needs an accurate reading below atmospheric pressure, absolute measurement is an option. One common example of using this type of sensors in industry when vacuum packaging is required, like in food industry to prevent food damaging. The third type is hydrostatic pressure measurement. Hydrostatic pressure, meaning the pressure that is exerted by a fluid at a given point due to gravity. So hydrostatic pressure sensors use this concept for measuring, meaning that when the density of the liquid is constant, hydrostatic pressure depends only on the height of the liquid. So the tank on the right would have a higher pressure. Therefore, they are widely used in indicating the level inside a tank based on the pressure readings as well as volume or mass measurements in liquids. Here are a couple of examples of different pressure sensors according to their measuring types. The physical device might look similar, but it's usually shown when selecting a pressure transmitter, the type of measuring principle for it. One of the common applications is to have pressure sensors used to measure, control, and regulate the pressure of steam. Steam can be a result of a process or used to heat different parts within manufacturing facilities. In the example you see here, the steam pressure is being monitored and the data from the pressure sensor is sent to a PLC. Then the PLC program uses the data to open or close a control valve to keep the pressure and steam regulated. Another common example is using pressure sensors in food industry, like milk and dairy processing, where pressure sensors are used in different stages to measure, monitor, and regulate product pressure inside the tank or steam pressure during any step of the process. Level sensors are common devices used specifically in fluid and chemical control systems. There are different types of level sensors, usually referred to as level transmitter. Level sensors are used to determine the level of liquid or granule materials inside a tank or container, then transfer status or data to a PLC. The output of level sensors are digital or analog values between 4 to 20 milliamps connected to an input module. This represents 0 to 100% of the level measured. One of the categories for level sensors is contact and non-contact. The difference is whether or not the sensor reaches the material. Examples of contact level sensors: float and capacitive level sensors. Examples of non-contact level sensors: ultrasonic and radar level sensors. Here you see a demonstration of the different types of level measurement, contact and non-contact. Each type works according to a different operation principle, and used for different applications. Depending on the manufacturer, level sensors are classified accordingly, as you can see here from Endress-Hauser. Level sensors are used in many industrial applications, like food and beverage, pharmaceutical and medicine, energy, and chemical processes. Another important classification for industrial level sensors is analog or continuous level measurement and digital or point or discrete level measurements. Here are examples from Siemens and Emerson. For continuous measurement, as the name indicates, the level sensors provide a continuous reading of the current level. The output of the sensor is analog, giving values between 4 to 20 milliamps. A continuous level measurement can be contact or non-contact type. This type of measurement is often used in food and beverage and pharmaceutical processes, where a continuous reading of the level measurement is needed. Ultrasonic and radar sensors are examples of continuous level measurements. For point or discrete level measurement, the sensor will only produce a signal at a specific point. For example, when it reaches a certain level, the output is either 0 or 1, and it's connected to a digital input module of the PLC. Here are a couple of examples of discrete level sensors. This is used in application like wastewater process. When, for example, we need to know if the tank is full in order to start the motor pumping the water out, or if the tank is empty, then open a valve to pump water in. In these two cases, we only need to know the level at a specific point. No continuous reading is needed. Here is an application of point level measurement using vibrating fork point level sensor. Ultrasonic sensors are one of the very common sensors used in industrial and manufacturing processes. Here are a couple of examples of ultrasonic sensors used within industry. An ultrasonic sensor operates by sending high-frequency sound waves towards a target and then measuring the time it takes for the pulses to bounce back. The time is directly proportional to the distance or the height of the object. The sensor uses the information to detect the presence of an object or to measure the distance to the object. It provides a non-contact measurement. An example here, an ultrasonic sensor is used to detect the presence of bottles on a conveyor belt. Here is another example, to detect the presence and height of solid objects inside a box. Ultrasonic sensors are commonly used in level measurements. The measuring principle is the same, that the sensor emits ultrasonic pulses, the surface of the material reflects the signal, the level is determined by measuring the time, and it's directly proportional to the distance traveled. The output is usually 4 to 20 milliamps, and it's connected to an analog input module. Ultrasonic level sensors are used both for liquid and solid materials, and can be used for closed tanks or open areas. Non-contact detection of objects is one of the advantages of using ultrasonic sensors. That means sensors do not scratch the sensing objects, resulting in a longer lifespan for the sensor and also protecting the target. This is valuable in processes like food and beverage industries. Also, ultrasonic sensors can detect an object indifferent of its color and transparency. For example, if two objects have similar shapes, even if one is transparent, such as glass, and the other one, for example, black plastic, they can both be detected with the same settings. Ultrasonic sensors also provide a larger detection area when compared to other sensors. This makes ultrasonic sensors very good choice during, for example, some chemical and corrosive processes, where the sensor needs to be placed a little bit further to protect the device. Thanks for taking the time to join me in this course. I hope you enjoyed the ride. This course gives an overview of the common sensors used within industrial automation system. To continue learning about automation system, I recommend checking out this course, Learn Industrial Automation, that goes through each level of the automation field. Industrial sensors are used to send information to PLC controllers. If you would like to learn more about PLC ladder logic programming, I recommend checking out the learning path, Become a PLC Developer. I look forward to seeing you in another course. Until next time, enjoy learning.